Hello everybody. This is one of the tutorials for Intro to Statistics, and we're going to run through the answers to some of the questions. But before we do that, and just as I'm letting extra people in, I've got a poll everywhere page, and you should be able to see the details on your monitor. You can go to pollev.com/Jenny Sexton 121, and my questions for the class are going to be on there. And I've just got a really kind of simple, enjoyable question first of all, and it's do you prefer cats or dogs? And it's just to illustrate the point between question 1 and question 2. So when you get on, you know, just select cats, dogs, or both, and then we'll move on to the next question. So we're getting a lot of dog people. If you've just recently joined, I've got a poll everywhere page, and the details for it are at the top of your screen. And the first question I've got for everybody, which is to sort of help us understand question 1 and question 2, is do you prefer cats or dogs? Okay, so we don't seem to have anybody else voting, so I'll just take you off shared screen. Okay. All right, so we've got a lot of people who prefer dogs. Now, I was sort of hoping that was going to be cats, but oh, yeah, we've got some more for cats. That's good. Anyway, so with that in mind, the next question, to start off with, you're only allowed to vote if you said dogs. So let's have a look at the next question, and I'm going to activate this one. So that should have updated now. You should have the question, how often do you go for a walk? And we should have only people who like dogs voting to start off with. And we've got a good number of people on there. Okay, that's sort of stabilized a little bit. So can I now invite everybody who said cats to also vote, and we'll see if we get which one kind of creeps ahead as we get people who vote for cats going forward. Okay, so we kind of got the result I was hoping for there, which was that when I asked the people who liked dogs to vote on how regularly they go walking, Lots of people said they would like going for a walk, and quite a few people said every day. And then as we added on the people who like cats, we got more people who only occasionally go for a walk. And why would that be? I guess it's because I'm choosing an unrepresentative sample when I'm asking about how regularly you guys like walking. When I'm talking only to the dog people, because if you've got a dog, you've got to take them for a walk, otherwise they're going to tear the house apart. So I hope that gave a live illustration of what the idea behind question 1 and question 2 was, is that, you know, if I only talk to a subgroup of you, in my example, the ones of you who like dogs, I'm not going to get an accurate representation of the whole class. So I took one of these classes on Tuesday morning, and I went a little bit too slow. I've also since then realised that you all actually have the solutions, so the solutions have been published. So what I'm hoping to do with the rest of the class is we'll start off looking at question number 3, and I'll work through it with you. You've got the solution, so you can look at the solution as we go along. If what I'm saying, if my visualizer is not completely in focus, you know, you can look at the solution that you've been given already. And then once we've seen that really quickly, I'm going to pin my screen as well so that you can see me. Okay. Yeah, rather than Sarah Lee's front room. Yeah, so once we've run through question 3, I've got a little bit of a variation on question 3 that we can all try together to sort of test our understanding. And then if we've got time, we're going to do question 6 as well. Okay, so let's go for the visualizer. Oh, and the other thing I should mention is please feel free to chat to each other in the chat. I'll try and remember to get on there as well. We should have a graduate teaching assistant here as well, who can answer any questions that come up in the chat, you know, while I'm distracted by answering the questions. Okay, so that's not really light enough. Okay. All right, so let's have a look at question 3. So the first part of question 3, we were actually given a population, and our population had 5 elements. So question 3, and we were given by Sarah Lees that our population had five possible values: 2, 3, 6, 8, and 11. Now, usually when we're looking at properties of samples, we don't actually know what the full population is, or it would be too time consuming for us to measure every single element in the population. But this question 4 and number 5 are all there to help us like sort of understand you know, some of the theorems that Sarah Lees has introduced for us. So the first part of the question was really quite straightforward. It said, what's the population mean? And the population mean is just the, you know, the mean in the sense that we understand, you know, the mean from probability 1 of all of the data points available. In this case, it's totally measurable and we can find out what it is, and it's denoted mu. As we go along, you're going to see lots of examples and situations where it's really difficult to measure mu because there's just too many people involved. What do I need to do? I just need to do the same as I would be doing with the mean, you know, that you did in high school or you did in probability 1. So I need to add up all of the elements and divide by the number of them that there are there. So I'm going to have 1 over 5 and then the sum of all of the elements in the population. So 2 plus 3 plus 6 plus 8 plus 11. Yeah, okay. And my answer should be 6. And part B, Again, I was asked for the population variance. I realise this is not very good. It's a tiny bit better, I guess. Not so good at night, I think. Ambient light. Okay, so we had the population variance. Okay, and this is denoted sigma squared, and it's the variance of these elements here. Now, when I calculate the population variance, I need to use, the factor n. It's going to be 1/5 that I'm multiplying by outside the sum. And the reason for that is because this is not a parameter that I'm estimating. This is the actual, oh, I've got somebody in the waiting room. Let me let them in. Okay. So the reason why I'm dividing by 5 outside my sums with the population variance is that this is something that's completely measurable. I can go to the population and I can measure each one. It's not something I'm trying to estimate. And when Sarah-Lise has given you 2 separate formulas for the sample variance, a biased one and an unbiased one, the difference between those is going to crop up later in week 4 when you start talking about, what's a bias estimate, what's not a biased estimate. So for the time being, we're going to divide by the number of elements in the sample 5, purely because this is an actual property of the population. It's not an estimated property of the population. And I need to sum up over the i's, the elements in the population, the x's, these ones, yep. Squared minus the sum of the x's, and then the sum all squared. So in this first term, I'm going to have 2 squared, 3 squared, 6 squared, 8 squared, 11 squared. And then in this one, this is the population mean that I've just calculated, so 6 squared here. So overall, I should have got myself to 10.8. Okay, so part C, I was asked about the sample distribution of the mean and the sample distribution variance if I pick a sample of size 2. So I've sort of got a little bit of a procedural way of approaching these questions. So the first thing I want to do is I want to write out all of the possible samples. Now, this is not necessarily practical. Okay, so somebody's asked, can I say again why it's 1/n and not 1/n minus 1? Really good question. So in this case, we're looking at the population variance, and the population variance, in this case, luckily, we can measure it exactly because we know what all of the elements in the population is. So it's a measurable property. It's an actual property of the population. Whereas when you've got your sample variance that you're looking at, you've got a biased and an unbiased version of the sample variance. And that's going to act as a proxy. It's going to, it's going to be a way of estimating what the actual variance of the population is going to be. And Sarah-Lise is going to get into that difference in week 4. So luckily, what does it say above the first sigma? It says there's a little squared there above that sigma, because sigma squared denotes the population variance. So, and this symbol here is a capital sigma as well. Just confuse the hell out of everybody. Yeah. So let me just, right, great stuff. Yeah, so somebody said omega. Yeah. Oh dear. Oh dear. You see, rusty with my Greek characters. So Charles is like, really helping us out with it's sigma for the top one, and it's so it's sigma for the bottom one and omega for the top one. So my procedural way of dealing with question 3 is the first thing I'm going to do is I'm going to list all of the possible samples, which in general is probably not going to be possible for interesting distributions or interesting problems that I've got to solve, but it is possible here. So I was given n is equal to 2. and I was told that I'm allowed to do replacement. So what I can do is I can pick, my first one could be 2, and the second number could also be 2. Or I could pick the first number's 2 and the second number's 3. And I'm going to have loads of these. I'm going to have 25 possibilities, I know. 2 and 6. 2 and 8. And 2 and 11. Along that top row. I'll just say 3, 2 here as well, just so that you can see exactly what's going on there. And 6, 2 here. Right. So hopefully you can fill in a table like that, and we should have in total, these are the possible samples. And we should have 25 of those. So I'm going to say m is equal to 25 because that's how many elements in that table I should have. Yeah. And the next stage is going to be to calculate the mean of each of these, because that's, you know, the property that I've been asked to calculate with. So for each of these possible samples, so I'm going to calculate the mean. I'm going to have, so X bar is going to be one of, and I'm going to have, again, I'm going to have a table with 25 elements in it. So this one's going to be, the mean is going to be 2. 2 plus 2 divided by 2. 2 plus 3 divided by 2 is 2.5, etc., etc. So I'm going to have loads of these. Okay, and 4. I'll just do the first line only. And this one, 10. 6.5. Okay. 3 here. 2.5 here. Okay. So that's the mean corresponding to this particular subsample of the population. Okay. And what I've been asked to find is what's the expectation of X bar. So if I picked one of these samples at random, and I took the mean, which would be one of these elements at random, what value do I expect to get? And what I'm going to need to do is I'm going to need to do the sum, and I'm going to sum over m because I've changed from 5 elements in the original population, so I had 5 elements in the original population, to 25 possible samples of size 2 in this table. So I'm going to be summing over m up to m, j equals 1, and I'm going to have let's go for 25. I'm going to go for m there. And this is m. So this is going to be one of these values, and then the probability that X bar is equal to m. So I should just be able to calculate from that point, but again, I like a table just to, you know, really double stress the points. So I've got possible means, m, and I've got the probability that they happen, X bar equals m. So just for the first couple in this table, I've got 2, 2.5, 3, 4, etc. Yeah. And looking at my table of possible values of the mean, I've got one entry in there that's 2. So 1 over 25 is the probability that X bar equals 2. And then for 2.5, I've got 1 here and 1 here. So I've got 2 over 25. What about the next one? Yep, so hopefully you were all thinking to yourselves, well, hopefully she's only got 1, 3 in that table. And I do, because it's on the lead diagonal, it's one of the elements. So whatever I add to 3, you know, the only other element in there that I could possibly combine to get a mean of 3 would be another 3. So I'm going to have 1 over 25 then. So you can continue filling this out, and then you can put your values in the sum. So into this one. And I'm really hoping that once you've crunched all of that, you should get EX bar is equal to 6. And with Sarah Lees's theorem about properties of the sample distribution should completely coincide with that. So what his theory was saying is that so the expectation of X bar should be equal to the population variance. So the expected value of the sample mean should be the population mean, mu. And that's exactly as we would have hoped, because we previously calculated that mu was equal to 6. So the second part of question C was to find the sample, the variance of the sample distribution. So we wanted to find the variance of X bar. Now, again, we need to look at all of the values in this table here that hopefully we filled out. And what we need to do is we need to do 1 over 25. Okay. I'm not going to jump to 1 over 25. I'm going to start, remember where I was going to start. Right. So I'm going to have m squared, and the probability X bar equals m minus this one. So the sample mean. All squared. Okay. I've run off the bottom of the page there. Please do poke me. Yeah, okay, Joe's poked me. That's great. Okay. So I do need poking when things fall off the bottom of the page there, because it's pretty rubbish with the visualizer sometimes. I just get completely carried away. Okay. So there we go. That's what I was saying. So the variance of the sample mean, this one, is going to be, first of all, we've got a squared term like we always do in the variance. We're going to have to square each of the possible values of the sample mean and times them by the probability that the mean has that value, and then subtract off the answer that we've already got, this one here, which is just this one here. So this is another reason why I like my table. Because when I'm asked to calculate a function of m, the expectation of a function of m in some way, what I can do is I can calculate that function first, and then you know, sum up over my new row multiplied by my probabilities of the occurrences. So what I could do is put m squared, and then 2 squared is 4, 2.5 squared, 9, 16, etc. And then just run through multiplying this one by this one, this one by this one, this one by this one, etc. and just adding up along the row in order to generate that first term. So what I should get is 5.4. And why would I get 5.4? Well, again, it's to do with looking back at Sarah Lees's theorem, which was about what's the relationship between the population variance and the variance of the sample mean. And what Sarah Lee's told us was that we should have, in this case where we don't have replacement without replacement, we should have bar X bar. So the variance of the sample mean should be the population variance divided by the number of elements in our sample, so divided by n. So in this case, we previously calculated that this one was 10.8. We've got 2 elements in our sample, which is 5.4, which luckily is exactly the same as when we ran through all of the possibilities and calculated the variance there as well. So you might say, okay, so if I can calculate the population variance, why on earth did I bother to write out all of the possible samples and calculate the variance of X bar? Why couldn't I have just used this formula from the very start? Okay, so Carmel has said we shouldn't have a squared in here, and he's totally right. I kind of got ahead of myself there. So here we should have the expectation of X bar squared. So with the square outside the sum. So I shouldn't have had a little square inside there at all. So that's great. So apologies for that little error there. Yeah, so coming back to this, I mean, like, you know, total, I would totally see your point if you're saying, why do we write out all of the list of all of the elements in the sample and calculate the variance of those means when I could have just used the formula out of the theorem? And you would be totally right. And the way that you would typically calculate or, you know, come up with, you know, what the, you typically wouldn't have access, you know, to what the population was. So you, first of all, we wouldn't necessarily be able to write out all of the possible samples because we wouldn't know what the properties of every single element of our population were. But the purpose of this example where we do it both ways is just to illustrate that that Sarah Lee's formula is correct and it's giving us the right values. It sort of gives us confidence that if we want to find a sample a variance of a sample and use that to sort of say something about what you know, the properties of the population, that things would be accurate. Yep. So. Right. Where we got to? Yeah. So question 4 and question 5 were very, very similar. So I can use the same kind of pragmatic approach. So I can list all of my possible samples. I can take the means of each of those possible samples. Again, I'm going to have a matrix or a table of those. And then I can use those to calculate the mean and the variance of the sample mean. I think you should in principle be able to do now question 4 and question 5 without any difficulty whatsoever. In the previous class, I then left people to do 3 and 4 and 5, and I realized that I was asking them to do something that they already had the answer to. So we're not going to do that, but I think I would just like to point out a couple of things about 4 and 5. So a good question I got asked on Tuesday about question 4 is, why do I not have to consider the order of the elements in the sample anymore? And I thought this was quite a good question. It says, we can limit ourselves to look at only 10 possible samples. Why on earth is this? So if I look back at the table that I've written at the very beginning of question C of the possible samples, if I do this without replacement, it's not possible for me to get anything on the lead diagonal. It's not possible for me to get 2, 2, because once I've picked 2 for the first element, I can't pick it for the second element. So all of these are going to have to go on the lead diagonal, which is going to leave me with 20 elements remaining. I hope it makes sense why there would be 20. It's because we've got a table of 25 and we've taken off the lead diagonal, so there would be 20 left. And then I can observe that everything above that lead diagonal, so everything here, is exactly the same as everything below the lead diagonal here. So I could totally, when it comes to looking at a table like this, still have 1 over 20 at the bottom here, and I'd have all of my elements would have at least 2 over 20, because above the lead diagonal is the same as below the lead diagonal. So because I've taken out that lead diagonal, every single value, every single possible sample in my sample space occurs in there twice. Once we're one way round, once the other way round. So that's why I can focus only on half of the table. So once I've taken out the lead diagonal, I can actually forget about everything below this lead diagonal, because it's all exactly the same as what's above here. So it kind of comes out in the wash. So if you don't feel confident about reducing the number of parameters like that, you can just leave it at the same table as you did before. And as you go through the calculation, your factor of 2 is actually just going to fall out and give you the same answer as if you are happy to jump in and not worry about the order of the elements in the sample. And question 5, I think the hint I would probably give there is just to, again, be quite careful with what your sample space, what possible samples you've got. So there's 10 possible samples. So that's possibly the best place to focus on is, what are the possible samples? So I want to give you guys some time to work on something. And because of that, I want to give you something that is similar, but not identical to something that you've already got a solution for. So let's take the sample from question 2. So the population from question 2. So population is going to be 2, 3, 6, 8, 11. Okay. And then take a sample of size n, sample size n equals 3, and do it without replacement. Okay, and can we calculate the expectation of X bar and the variance of X bar? So give that a go, and I've got 2 questions on my poll and everywhere page to sort of help us along with that. So my first question is, which of these is not one of the possible sample means? So it looks like you're going to have to do a little bit of work before getting there. So I'm just going to have to go answer the door. So I'm going to leave you to work on writing out what all of the possible samples are in this case, and also then answering this question. Oh dear. So is anybody going to be bold and vote for one of those three options? Now, all of them should be divided by 3. So let's see if I can update that live. So is anybody else willing to commit? Oh, Pedro, I'm sure you're not really bad at this. So why don't we all start doing it together? So what I'm going to have is I'm going to have, first of all, step A, write out the possible samples. So I've got the first one, I could pick 2, 3, 6. Yep. I could also pick 2, 3, 8. And I could also pick 2, 3, 11. And can you find 7 more of those possible samples? Right, Kamal says, sure, no problem. Okay, so once you've written down those extra 7, the second part I'm going to want you to do is I'm going to want you to find the mean of each of these. So, for example, this first one's going to be 2 plus 3 plus 6. So it's 15 divided by 3. Okay, and then this one, I'm going to have 8 plus 2 plus 3, 30 divided by 3. Oh, that's not right, is it? Oh, damn it. Oh, I like. This one's 11 over 3. It's 5 and 6. 11 over 3, 13 over 3. And then what about this one? So 16 over 3. So why did the order matter for 1C but not this one? So the order matters when we're picking with replacement, but when we're picking without replacement, the order doesn't matter. And the reason for this is because when we wrote out all of the possible permutations, in the previous example, we could fit them in a table and we could see the symmetry around the middle line. But even when we're selecting from more than 2 elements, we'll still have the same type of symmetry. So if you wrote out all of the possible permutations, even, you know, you could group them. You could say, oh, so the combination, let's think about how we could actually practically get this. If we picked 2, then 3, then 6, we'd get this combination. We'd also get this combination if we picked 3, then 2, then 6. Or if we picked 2, then 6, then 3, etc. Yeah. So, and the mean in all of these cases is going to be the same. So the mean is always going to be 11 divided by 3, regardless of what order I put the elements in. And then I'm just going to have a factor. So I'm going to have, for each one of these 10 that I find, I'm going to find 6 different ways of ordering the 3 elements. So I'm going to have to divide by 60. Whereas, you know, I would prefer to just divide by 10 and have less samples to think about. Okay. So hopefully you've got your 10 possible samples, and hopefully you've also got 10 possible means of those samples as well. Now I've only given you 3. And I'm just going to see how many votes we've got on my question, see how we're going with the question. Okay, so do I still only have one person pitching in for 15? Okay, so I've ruled out 16. I know that 16 isn't the answer to my poll everywhere question, because so 16 divided by 3 isn't the answer, because I found one of the samples that actually has that that mean. I found that this possible sample has a mean of 16.3. So I know I'm fine with that. Can I ask, is everybody stuck? Would anybody like to commit to that? You know, you can raise your hand, you can say, click yes or no in here, or you can just write directly to me. Yeah, so Carmel saying pretty much, yes, we're stuck. Fine, that's great. So rather than skip ahead to number 6, then what I'll do is I'll do this in more detail. So what I asked you to do is I asked you to take the population from question 2 and then answer a question that was very much like question 5. So the first thing I asked was what's the expected value of the sample means, what's the variance of the sample means. And in order to do that, the first thing you need to do is you need to know what the possible samples are. Now, I think there's going to be 10 of these, and I deal with the situation as though the order of the elements in the samples doesn't matter. And the reason why I do that is because when I take the mean is going to have the same value regardless of which order I picked the underlying points in. So for a full answer for question A, I'm going to have 10 elements. I'm going to have 2, 3, 6, 2, 3, 8, 2, 3, 11. I'm also going to have 2 and then 6 and 8, so missing out the 3, 2 and 6 and 11, and I'm also going to put 2, 8, 11 there. Yeah, so with this one I've missed out 3 and 6 and then gone on for the rest of them. Now those are just the ones that contain a 2, so the first 6 there contain a 2. I've also got the possibility of 3, 6 and 8 and 3, 6, 11 and 3, 8, 11. And then my final one that doesn't really match, neither has a 2 or a 3 in, it's got 6, 8, 11 in. So these are my possibles. So those are my possible samples of size 3. Okay, now what's the mean in each of these cases? Can you tell me what the mean is going to be? So the mean of this one here is going to be 11 over 3, because I add up all of the elements and divide by 3 because I've picked out 3. Same with this one, add up the elements, divide by 3. I've got the 13.3. So 13 divided by 3, and with this one here I've got 16 divided by 3. Just to do one more, with this one here I've got 2 plus 6 plus 8, 16 over 3. Okay, so can you finish those off for me? I'm going to do that final one as well. I've got 11 plus 6 plus 8, 25 over 3. And then if you do the other 5, there should be one value that's that you don't find on my poll everywhere question. Yep. Are we a bit more clear about what's going on now? Carmel, can you tell me whether you get it now? Joe says he understands now. Carmel says, yes, I've got it now. That's good. That's good. Okay. So when you found those means, vote on the poll anywhere question as to which one you don't find in your table as a possible mean. Okay. All right. So when I want to calculate what the average of these sample means are, what I've got is I've got 10 elements here. So I'm going to have 1 divided by 10. And then I've got all of these possible mean values. I've got 11 over 3, 16 over 3, 25 over 3, etc. So I have to add up all of the possible values of of the mean that I've calculated by writing out all of the possible samples. So I'm going to have 11 divided by 3 plus 13 divided by 3 plus 16 divided by 3 plus 16 divided by all of them. And I would really hope that Pedro says he's voted now. That's amazing. So I hope a few more of you can commit. Now, you know, one of the nice things about these poll everywhere things is that you can pile on a little bit. So if you're not 100% sure, but you think the answer's 15, you can sort of wait a little while and see if a couple of other people go for 15 and then think, I feel a bit more confident that the answer's 15 and jump on as well. You can sort of like wait for somebody who's a smarty pants to get in there first and just like be like, I'm not going to commit until somebody else does. You can definitely do that. Going back to or coming back to your review, I've got the expectation of X bar. I need to take the expectation of all of those means that I've calculated. And when I calculate the variance of X bar, again, I'm calculating the variance of all of the means that I calculated when I wrote out what the samples are. So what I'm going to have is I'm going to have I'm going to have to do, first of all, I'm going to have to sum them. I'm going to have to times each of them by 1 over 10 because I've got 10 possible options. And I'm going to have the sum of m squared. So I'm going to have to square each of these. So 11 over 3 squared plus 13 over 3 squared, etc. And this is where, you know, R comes in really, really handy because, you know, nobody really wants to calculate all of these values and take the square of them, etc. But you're going to be in this situation where you're taking the square of each of the elements and dividing by 10 and then taking off the square of the expectation of X bar that we've found there. So I've got 3 more in the waiting room. Right, I have most definitely run over. So I'm assuming that I'm having some people joining me who are here for the class that's directly afterwards. So I've also got a 5 o'clock starting. But before I get onto that, if anybody here is still here from the first class, I'm going to zip on through a couple of questions on poll everywhere and just ask you guys if you can help me with this next one. So just let me know, do you think we should use it again? Do you like it, basically? I liked it because it helped me know when you guys got stuck. But just very quickly, just let me know before you leave by voting on my poll, whether you think we should use it again. If you're just joining me for 5 o'clock, you're possibly looking at my visualizer and thinking, oh my good Lord, what is she talking about? That's because I've got a class, exactly the same class directly beforehand. So don't worry, I'm going to take that off. Okay, have we had a bit of a turnaround? Are we all here for 5 o'clock, or is some people staying who've been here since 4 o'clock, or what's the situation? Everybody's very, very welcome. So welcome if you're just joining. I'm just going to give the 5 o'clock lot another 5 minutes to join. As you might have been able to hear there, it's my baby in the background. So I'm going to go see what's going on. Okay, everything's all right. Hello, so as you're all joining, I expect that we'll have a few extra people joining us because the previous class was about 45 people. I have first of all, I'm not Sarah Lees, as you might be able to see. I'm taking the 4 till 5 class, and also the 5 till 6 class today, and 9 till 10 class on Tuesday mornings as well for this course. If you've got any questions, feel free to email Sarah Lees or call him. However you see fit. You can also ask me, of course. Now, the key thing we've got is I've got a poll everywhere page. The details should be visible to you. And my first question there is kind of trivial, but might be quite exciting to know what the answer is. So, which do you like best, cats or dogs? And I've left an option there for that. Why can't I pick both? Which I think would probably be my response. Why can't I pick both? So the first thing you need to do for this class, leave it open the entire time that you're in class, is get on Poll Everywhere, get on my page and start voting for cats or dogs. It's going to help us answer, it's going to help us understand the answer. So, oh, nobody says cats yet. So to anybody who's new joining, I'm taking your class. My name's Jenny. I've got a Poll Everywhere page, and the first thing we're going to do is we've just got really silly questions. I'm just asking you guys, do you like dogs or cats, or can you just really not decide? So get on my Poll Everywhere page and click A, B, or C, and the details are just laid on the top of your screen. And so far, we've got a lot of people who like dogs and a few people who like cats who can't choose. So. Seems like we're nearly all here. Oh, a couple more. So the first thing I've got for anybody who's new is please go to my poll anywhere page and decide whether you like cats or dogs best. Okay, so looks like we've got nearly everybody on. That's my baby. Hopefully my partner's going to go get him. I don't know why I said him, it's a her. Anyway, yeah, so hopefully my partner's going to go get the baby. Hopefully I don't have to do that. Okay. So we've got loads of people piling on now with the cats and dogs question. So, you know, please go to my poll everywhere page. Please vote cats or dogs. It's going to help us understand question 1 and 2. So when you've done that, it seems like we have a lot of people on the dogs front, and we did last lesson as well. So maybe I picked this question like not quite right, really. I think somebody sent something to me in the chat. So yes, this is the supervision for intro to stats. And this question is going to help you understand question 1 and question 2 on exercise sheet 2, hopefully, fingers crossed. So I'm asking cats or dogs, and I think I've nearly got everybody voted. So my next question is going to be, and I want only the people who answered dogs to answer first of all, okay? So pile on, if you answered dogs, tell me how often you go for a walk. I need to activate it. Bit difficult for you to answer if I don't activate it. So we're going for only the people who answered dogs first, and asking how often do you go for a walk? And I want to see only people who answered I like dogs best answer about how often they like going for a walk. Okay, I really hope that everybody who doesn't like dogs better than cats actually has a dog, because some of those dogs are going to be like really sad and not being taken out every day. But anyway, now that we've established that even those people who like dogs better than cats don't actually walk that regularly, let's get everybody, so everybody who said I can't decide or I like cats, to join in as well and see whether that affects the outcome at all. I'm hoping it does affect the outcome, although the people who prefer dogs were kind of disappointing me by not walking as regularly as I would hope. This has totally not gone the way that I was hoping. Because I was kind of hoping that if you said you like dogs most, that it was more likely that you had a dog. And if you had a dog, then you'd have to go out every day. And so I was hoping that when we asked the people who like cats best to join us as well, that they'd pile on that they didn't like walking. And we would immediately see that it's not really representative when talking about how regularly we go for a walk to limit ourselves to only people who have a dog, because it's kind of, yeah. It's kind of important to walk your dog every day. If you had a dog, you'd know that this is really important. My dog would hate it if I didn't take him for a walk. Okay, so what I was trying to do with that question is I was trying to illustrate whether samples are representative or not. It didn't quite go as planned. It did go to plan at 4 o'clock. So you guys are obviously the exception rather than the rule. So I'm going to stop sharing with you guys and move over to my visualizer. What we're going to do, what the plan is for today is we are going to do question 3 all together. And I realise that you've been given the answers to your questions already. So I don't want to then leave you to do some of the other question 4 and question 5 like I did on Friday morning, because I know that you've got the answers. So instead I've got a question that's similar to question 3 and question 5, and we'll run through that together. And I kind of noticed in the previous class at 4 o'clock that there was some confusion about this. So hopefully, you know, the things that I picked up at 4 o'clock, I can incorporate those in and help you guys understand, and we can kind of get through together. So, question 3. If I get time, I'll go on to question 6, but I really don't think I'm going to get time to go on to question 6. So question 3, what we were talking about is the first part of the question was we were given a population, omega, and we knew that there's 5 possible options. We've got 2, 3, 6, 8 and 11. Now, often in real life, or often further on in the course, you know, you're not going to know what the population is. You're not going to be able to go out there and measure every single element in the population. There's just going to be too many of them. But this question and question 4 and question 5 are structured in the way that they are to sort of help us understand the connection between the population properties and the sample properties, so that we can, you know, have a better idea of, you know, why it's okay to focus only on the sample, or what kind of transformation we need to do to get between the two. So the first part of question 3, we were asked, what's the population mean? Okay. And this one is, we just calculate this exactly the same as we calculate means in probability 1. So I need to calculate the mean of these 5 values. So I'm going to have my notation for the population mean is mu, and I've got 5 elements. So I've got 1 over 5, and then I add up these 5 elements. So I've got 2 plus 3 plus 6 plus 8 plus 11. And I should get 6. Okay. And the second part of question 3, part B, I was asked for the population variance. Okay, and this is denoted sigma squared. And what I need to do with this is I need to do 1 over 5, and I can do 2 minus 6 squared plus 3 minus 6 squared plus 6 minus 6 squared plus 8 minus 6 squared plus 11 minus 6 squared. Now here I'm using, you know, the idea that, that sigma can be expressed as the expectation of x squared minus the expectation of x all squared. Now you could just calculate those two things separately and take the difference between them, and you'd get exactly the same result as if you calculate like this, which is, if we do this. Yeah. So so McAllis is saying, so it's the same probability that we choose each of these elements. So yeah, that's what we're trying to say. Is we're trying to say if I picked one element, you know, what's the average possible value of that one element that I would pick. So there's five items in my population, so I need to divide by 5. Yeah, okay. So in the Tuesday tutorial, somebody asked me at this point, okay, so why are you dividing by 5 and not by 4? Sarah Lees has given us these 2 formulas for the variance. One of them says divide by n, and the other one says divide by n minus 1. So why do I use the divide by n one? And this is a really good question. And the answer is that here we're looking at the properties of the population. So it is a variance that we can actually measure because we know what all of the values in the population are. So we don't need to worry about a biased or an unbiased estimate for the variance, because this is the actual variance that we're calculating. When we come to looking at a sample, so a subset of the population, when we calculate the variance of that sample, we might be interested in whether or not that's a biased or a biased or an unbiased estimate of the population variance, and then we'd have this issue of whether to divide by n or n minus 1. So Sarah Lees goes into a lot more detail about that in week 4. So for the time being, put to the back of your mind dividing by n minus 1. Don't worry about it too much, and you'll get a much more detailed explanation of when and why you need to divide by n minus 1 in week 4. Okay. So the value of the variance that you should have got if you calculate this is going to be, I wrote that down, 10.8. Okay. Now, so far so good. Raquel says, so n minus 1 for samples and n for the whole population. And essentially, yes. You'll see in week 4 that if you use n for a sample, you get a biased estimator of the actual population mean, and Sarah Lees will show you why that is. Now, that doesn't mean that you might not in some cases divide by n. It might be that dividing by n and dividing by n minus 1 are very, very close because n is very, very big. But he'll give you a definition of what biased actually mathematically means and why it means we've got to switch to n minus 1 in week 4. So that's sort of coming up for us. Okay. So we're confident to go on to part C now. So I've noticed from what happened in the previous class that a lot of people find part C like quite tricky, and they found my explanation of it quite tricky as well. So I'm going to try and improve on my explanation. So the first thing I've been told is I need to take a sample of size 2. So n is equal to 2. And I take a sample, and the question is then about, some properties of the sample. So what's the sample mean and what's the variance of the, so what's the expected value of the sample mean and what's the variance of the sample mean. So the first thing I want to do is I want to list all of the possible samples in this case. So because I'm doing it with replacement, if I pick out one of the elements for the first element, I'm allowed to pick that same element for the second element. So I'm allowed to pick, so if I pick 2 first, I can then pick any of these values for the second value. So I can pick 2 or 3, or, yeah. So the first thing I do is I write out a table of the possible samples. Okay. Now I'm hoping that there's going to be 25 elements here. So I'm going to have 2, 2, 2, 3, 2, 6, 2, 8, and 2, 11 in my top row. In my second row, I'm going to have 3, and then 2, 3, 3, etc. This table has m equals 25 elements. So when I pick two elements of my population, of this population here, when I pick two, there's 25 ways of me picking two elements. So I'm going to write those out into a table. And then the next thing I do is I've been told that I'm interested in the sample mean. So the sample mean is going to be a random variable because I don't know which sample it is that I've picked. So what's going on with that is I'm going to have, if I pick a particular sample, so if I picked if the combination I picked was 2, 2, and I took the mean of my sample that I actually selected, 2, 2 would be 2. If I happened to pick 2 and 8, then the mean of the sample that I'd picked would be 2 plus 8 is 10, divided by 2 is 5. Okay, but I don't know which of these values I actually pick. So what I'd like to say, oh dear. So the second thing I'd like is a table of the possible sample means, which is a random variable, because it's a random variable because I don't know which sample I'm going to be picking. And there is 25 of them again, which should directly correspond. Right. That's better. Okay. So for each of my samples, I've got a sample mean. In this case, I'm going to have 2.5. In this case, I've got 2 plus 6 divided by 2 is 4. So again, I should have a total of 25 possible sample means. Okay. Now, each of my samples is equally likely to come out. So each element in this table is equally likely to be picked. So if I wanted to calculate the expected value of these sample means, what I could do is I could add up all of the elements in this table of 25 and divide by 25. But I've got some duplicates. So looking at the table of possible samples, I've got 2, 3 here, and I've got 3, 2 here. And both of those, the mean is 2.5. So I've got 2.5 cropping up twice in this table. I've got 2 cropping up only once, and I've got 3 on that lead diagonal. Hopefully 3 is only going to be in there once. But I think this one is going to be 4, because this one's going to correspond to picking 6 and then 2, which again is 4. So I've got some symmetry around this main line. Now, because I might not have listed the possible subsamples in the most logical way, like I have here, one thing I can do is I can create myself a table of the possible sample means and their frequency in this table, and I can use those to calculate the expected sample mean. So this kind of intermediate step you maybe don't need. You might be happy going directly from your table of possible samples to the table I'm about to draw, or you might be happy to just do a table of possible samples and then a table of possible means and then calculate the mean directly from that. So, or you can do all three if it reassures you. Now, with these things, definitely it reassures me to get the duplication in there. And the reason for this is I really hate calculating. So I know I'm never going to be particularly accurate if I have to put a whole sequence of numbers into my calculator, especially under exam conditions. I would probably have to do that 2 or 3 times just to make sure that I didn't press the wrong button at some point, because I am always pressing the wrong button. Now that might not be you. You might be really confident using your calculator. So if that's the case, then you should use a method that skips any steps that you feel is redundant. So my next table is going to have M. So this is the possible sample means. Okay. Yeah, I'm going to go with M, and I'm going to go with the probability that X bar equals M. Okay. I've used some duplicate notation here, so I think maybe I should have a capital M, so to denote the number of elements in my table rather than a little m to avoid confusion. So I've got the lowest possible value is 2, and it's cropping up only once in this table. So there's only one possible subsample that one possible sample of size 2 that I can pick that results in having a mean of 2. So I'm going to have 1 over 25 because it's in my table here once. The second one, I've got 2.5, and this crops up twice. So once here and once here. So I'm going to have 2 over 25. And we've got loads of possible values there. You've also got 4, 5. I think you've got 4.5 cropping up. 6. You've got loads of values there, okay? Some of them crop up with frequency 1, some of them pop up with frequency 2, and one of them pops up with frequency 4, so 7 comes up 4 times. Aside from 7, what we've got is we've got the lead diagonal here where we pick the same number twice. This is the same number twice on our lead diagonal. Those only crop up once. So mean 3 is comes in the table once. So I use the probability 1 over 25. Whereas and 2 only crops up once. It's on that lead diagonal. Whereas all the other numbers come up twice, so we have 2 over 25, or in the case of 7, 4 over 25, because it crops up 4 times. So when I want to calculate the expectation of X bar, what I need to do is I need to calculate the sum over the possible values of M. So I've got, so I need to sum up over the M. I've got 25 of them in total, and the probability that X bar equals M. So in this sum, the first term I'm going to have is 2 times 1 over 25 plus 2.5 times 2 over 25. I'm going to have 3 times 1 over 25, and then with 4, 4 times 2 over 25, etc. Okay. And hopefully, if I get all of that into my calculator correctly, I'm going to get 6. So when you look at this, what you should be taking away is that the population mean that you get when you just were able to observe all of the values and calculate the actual mean of the population would be exactly the same as your expected value of these sample means. So if you took loads and loads of samples of size 2, in each case you took the average, then those averages, would be roughly, the population mean overall. So our takeaway should be that this completely coincides with Sarah-Lee's theorem, that where he showed you that the expectation of the sample mean is equal to mu, the population mean. So this is verified, so we've checked it's right in this case. Okay. Now, the second part of question C asked us to calculate the variance of X bar. And we do it really, really similarly. So we've got our table of the possible X bars. We've got the expectation of X bar, which is going to help us. So we know that this is going to be the expectation of X bar squared minus the expectation of X bar squared. So we know what this bit here is. We know this bit's 6 squared already. So the bit we need to focus on is this first sum here. And what we can do with that I want to add on to here. I just want to say, right, so we're going to do the expectation of X bar squared. This one. What we need to do is we need to square each one of these. So we're going to have 2 squared, and that's going to occur with frequency 1 over 25, so divide by 25, plus 2.5 squared. And we've got 2 of those, so we need to times by 2 and divide by 25, etc. Okay. And what you should get overall is you should get that the variance of X bar is equal to 41.4. Now, no, you shouldn't. You totally shouldn't. You should get that the value of this is equal to 41.4, which leads you to a variance of 5.4. And again, this coincides with Sarah-Lee's theorem, because Sarah-Lee's theorem was telling us that the variance of X bar is equal to the population variance divided by the sample size, which in this case we know is 10.8 divided by 2 is 5.4, which is exactly how we would expect. So you can check that your answer is right using Sarah-Lee's formula, Sarah-Lee's theorem for this week. Okay. So the next really good question that I got, but in both the previous 2 classes, was about question 4. So in question 4, we were told we're going to do the same question but without replacement. So I'm just going to let somebody in. So in the case when we do this without replacement, we're going to follow a very similar method. So I'm going to go back to my solution for this one, but we're going to have to change the possible sample, the table of possible samples. So if it was without replacement, I wouldn't be able to get 2 and 2, because once I'd picked 2 from the overall population, the 2 would be gone. And the second number I could pick would only be one of the remaining ones. So that's going to make anything on the lead diagonal of my table of possible samples not possible anymore. So with question 4, a sample which is 2, 2 or 3, 3. Or 6, 6, etc. are not possible. Which leaves me with 20 possible samples. Okay. And I can just reuse the table I had before, but without those lead diagonal points. I would just need to change my capital M to 20 because I'll have deleted 5 elements out of this table. But the question that I was getting was, but in Sarah-Lee's solutions, he says that the order doesn't matter. and that I can just think about 10 possible samples. Why is that? And the answer to this question, you can see just by looking at this table and then looking at the table of sample means. So because we're looking at a sample mean, that's the property that we're trying to examine, it doesn't matter whether we pick the sample 3, 2 or 2, 3. When I calculate the sample mean, it's going to be the same in both cases. So because of that, I can focus on only the values either above or below that lead diagonal. So I could just continue the same way as I did with question 3 with all of those 20 elements there and all of the 20 possible samples there. And I'd end up dividing by 20 because when I'd have my table of the frequencies, each of them would be divided by 20. But what I would find would be that I'd have 2 of every single element except for 7, where I would have 4. So I could simplify the probabilities in that bottom row to 1 over 10. And that just demonstrates that it's totally fine in the case without replacement for me to discard half of this table of possible samples because in terms of the mean, the elements below the lead diagonal are exactly the same as the elements above the lead diagonal. Now, things might get a little bit tricky if I was dealing with a property other than the mean or the median, because it might be that the order of the sample does matter to the property that I'm looking at. But most of the time, I would be totally fine with just dealing with the unique in terms of mean elements of that table of possible samples. So I hope that makes sense as to why I'm allowed to divide by 10 in question 4. So what I wanted to say about that, as I take out the elements on the lead diagonal because they're not possible, I've got 20 possible samples remain, and I can continue like that. Or look at the possible samples with order not important. And in this case, I'm going to have 10 possible samples. And I get exactly the same result. So it's just whichever you feel most comfortable with. So at this stage, I want to do something a little bit like question 5, but I want to change the population to being the same as what we've dealt with here in question 3 and question 4. So question for you guys. So take omega is the sample that we've got, 2, 3, 6, 8, and 11. And list the possible samples of size 3 and equals 3 without replacement. And hint, there's 10. Okay. So I'm going to give you guys a couple of minutes to do that. When you've written them all down, or once you've managed to write them all down, if you could direct message me and just say done. Once I get a couple of those responses saying done, I'll move on to what we need to do next. Okay, so I've got a few people who've said they've managed to get there. So let me help anybody out who's still going by writing them out. So we've got 3. Copying the wrong thing. Okay, so you should have got those 10 possible samples of size 3. Okay, so the next thing I'd like you guys to do is to calculate the mean for each of these samples. Okay, and when you finished that one, I've updated the question on my poll everywhere page, and it says which one of these 3 values is not one of the possible means. So try and see if you can just answer that question as well, just so we've got an idea of when you finished and whether you've noticed which one of the possible answers I've given you is not one of the possible sample means. So I've just done the first one there for you. We're beginning to get a little bit of a consensus there on which one is not one of the possible sample means. We've got quite a lot of people saying that 15 isn't, and you'd all be right in saying that 15 isn't. So again, I would have 10 possible sample means. I've got 11 over 3, 13, 16. I'm going to use the same layout as this just so that you can see how they correspond. 16 again, 19 over 3. Oh dear, what the hell am I doing? 13. 21 divided by 3, 17, 20 divided by 3, and 22 divided by 3, and 25 divided by 3. Okay, so at this point I'm ready to calculate what the expectation of X bar is. So the sample mean is a random variable. It's in this table. It is one of these values, and each of them are equally likely. And the next thing I want to do is calculate the expectation of X bar. So how I would want to do that is I've got 10 elements in there, so I'm going to want to divide by 10. Each one of them is equally likely. And then I'm going to add up each of these possible sample means. So I've got 11 over 3 plus 13 over 3, etc. Okay. And hopefully, if I do that, my answer is going to be 6. Now, similarly to question 3, if I want to calculate the variance of the sample means, so the variance of X bar, the first thing I'm going to need to do is calculate the variance of X bar squared, of the square of X bar, and then I'm going to have to subtract off the expectation of the sample mean, so the expectation of X bar. I already know what this one is. I already know that this one is 6. So my key problem is going to be to calculate this term. So give that a go. Can you calculate the expectation of the square of the sample means? So that's the expectation of the square of these elements here. When you're done, my next question on Poll Everywhere is what's the sample distribution variance? So what I'm asking for is what's the variance of X bar? So when you found that number, it's one of those items on the list. It's either 1.8, 10.8 or 4.05. Have a vote as to which one you think it is. And I'm expecting that to be moderately difficult. Yeah, I'm maybe going to have to give you a few minutes to give that a go. So give it a go. Yeah, so somebody's noticed that I've missed a square off here. So thank you very much for pointing that out. I'm sure I'd squared it in my mind. So, yep, I definitely need to square the expectation of X when I take it off there. So I need to take off X squared. The poll isn't active yet. Oh dear. There we go. So which one of those values is the variance of the sample means, is the sample distribution variance? And I do want to point out that I've actually got Poll Anywhere set up to be completely anonymous. So unless you put your real name in when you go to my page, I can't tell who has voted for what. So just give it a go. Doesn't matter if it's right, wrong, crazy, just give it a go. Okay, so it seems like I might have managed to catch out a good number of you. In fact, I've managed to catch out approximately half of you because the answer is 1.8. The answer 4.05 is actually the answer to question 5, where you've got a slightly different sample than I've given you here. So well done everybody who actually answered question 5. But the answer to the question that I just asked you, so to do question 5 with the sample from question 3, the answer is 1.8, which 56% of you have actually got. So I realise that I've overrun because these classes are meant to be exactly 45 minutes long. So I've just got one extra question for you, it's really simple. It's, should we continue to use poll everywhere? Do you like it? So if you could, just before you leave, just answer that question for me. Just tell me whether you think it's a good tool or not. I'm at the moment thinking it's good because it's helped me in the 2 classes to gauge where you guys are up to and react to where people have got confused. But if you don't like it, if you think, oh, I'm really over all of this interactivity, you know, that's totally fine as well. So feel free to leave now if you want, but if you please could just vote and let me know whether you want me to keep using this poll everywhere, that would be amazing. Yeah, and I will see you all in a fortnight's time because I don't do the R tutorials, which are on the even numbered weeks. I am only teaching on the odd numbered weeks. So I'll see you all in 2 weeks' time.
Thank you.
You're welcome. Hello, Solis.
Oh, hello, Johnny.
How are you?
I'm okay. I just was
Hi,
taking.
Professor.
Okay.
I just want to ask that will the answer of the problem 6 and 7 will be posted on the blackboard?
I think they are already on Solis' webpage.
Well, I only posted them today, but I posted the solutions earlier today.
Yeah, all of them were published earlier today.
Yeah. Yeah, because today is the last week. I mean, last day of tutorials. So, yeah, it should be.
Okay, thank you so much.
Sorry.
Thank you so much. Appreciate that.
All right, great. Have a good day, man. Have a good day. How are you, Jenny? You okay?
Yeah, I'm good. How are you?
Not bad. I mean, just sometimes tiring because, yeah, because I give them like a weekly assignment.
Yeah.
Yeah, it's kind of is so. I gave them the answers today for the weekly assignment.
Okay.
Yeah.
So this counts, does it? Is it like 1% a week or something?
Yeah, 1%. Yeah.
Okay, that's a nice way of doing it, actually. Sort of like to participate.
So, you got a lot of teaching to do, or is it? I mean, how many hours do you do?
And I'm only part-time, so I do 6.
Okay, that's not bad.
Yeah, I just had a baby just before.
Yeah, I heard the sound.
You heard her crying, yeah. Yeah, I only do part-time because of that. It still feels like quite a lot to do. But maybe that's because life gets in the way.
Yeah. Do you live far from? Are you in Manchester or somewhere else?
I used to live in Manchester. I used to live in Fallowfield, but now I live in Todmorden in West Yorkshire.
Oh, okay.
But it's actually really close to Manchester. It's about 25 minutes on the train.
Oh, okay.
So it's, well, when I used to work in town, it would take me the same amount of time as commuting from Fallowfield. Are you very close to the university?
Yeah, I live very close, like only like 10 minutes walk, maybe less than.
Okay.
Yeah.
I think it's the first time I've met you, even though I was a PhD.
Yeah, I might have seen you around, but I don't. I might have. You did your PhD with Peter, right? Peter, is it Peter Duck? Or?
No, it was Goran.
Oh, Goran. Oh.
Yeah.
Oh, okay. I didn't know that.
But it's a long time ago. I finished in 2014.
Oh, okay.
Yeah, so yeah.
I've been around since 2006. So I probably seen you somewhere, but I can't recognize.
Yeah, but there's hundreds of us in that time.
No.
Well, it's been really nice teaching your classes.
Okay, thank you.
I really appreciate having all the solutions in advance and everything.
Yeah, I normally post things on a Thursday. Like today, I did it a little bit earlier than usual, but normally I post them like in the afternoon or evening of Thursday. Yeah.
All right. I did notice one thing is that on your final question on this exercise sheet, it says little x1, little x2 up to x5, but then you've given 6 different.
Oh yeah, that's a mistake. Yeah.
Yeah.
It should be x1 to x6. Yeah, you're right. Yeah.
Well, I figured I maybe wasn't the first person to point that out to you.
Yeah. There are several students asked me that question.
Yeah, I just wanted
pointed that out to me. So, and I told them.
Not important. It's very, very small, and I didn't find anything else. Everything else. Really.
Okay, thank you.
So, when I come back for week 4, if there's any particular question that you think I should focus on, if you just let me know.
Yeah.
Sort of don't want the stress of my class.
No. I mean, I don't do polls like you do, but I mean, I try to go through question by question, and I don't know whether the students like my way or don't. I don't know. I don't really know. Maybe they like your way, I guess, because you do polls, and maybe the students like seeing polls. I don't know.
Yeah, well, I'm still working on it a little bit, but I kind of want to get them to do some work as we go along rather than just.
Yeah.
But I think with the 4 o'clock one, it didn't work so well because I asked them to do too much and didn't break it. Huh?
Because because for me, I thought doing polls may take up your time, so I may not be able to finish all the questions. Like normally, I am able to. Like this week, I covered 6 out of the 7 questions. And sometimes, a couple of times, I did all the questions.
Wow.
A couple of times, I did all the questions. And
I would have to seriously speed up to cover all of the questions.
so I mean, if I use polls, then that will take too much. It will delay things, you know what I'm saying?
Yeah, no, I do.
Yeah. So I don't know.
Yeah, well, maybe, if you're still going to try and cover all of the questions, if there is one that you think like, oh, if she's going slow, she can miss this one off.
Yeah.
Something like that. I
Yeah.
still really appreciate you letting me know which ones are most important.
Okay. I will let you know.
Thank you very much.
Yeah. So are you staying with Case or no? You don't. You're not related to Case, are you? No.
I used to live with him. I don't anymore. It's not his baby.
Okay. Sorry. I'm sorry.
That's okay. About like when he first came to Manchester, we were together, I think about 7 years after he first came to Manchester. But we've been split up about 2 years, something like that.
Okay.
Yeah, he's kind of he's if it wasn't for lockdown, I think he would be here a lot because we still share a dog.
Okay.
So we know each other quite well.
Okay.
Yeah, but yeah, no, I don't live with him. No.
Okay. Have a good evening and
yeah, okay. Well, I'll speak to you maybe in a couple of weeks' time. So
yeah.
right, bye.
Bye.